Hello, my name is Levente Koncz. I work at Shaper 3D, and I'm going to talk about how we use open source software at Shaper 3D. I have a few intro slides, and I will cherry pick a single library, and I will tell you about the good and the bad experiences we had with this library. So, for those of you that don't know, Shaper 3D has a single application. It's a CAD application, a solid modeler, with all the usual solid modeling features like surface analysis and technical drawings. And you can go to App Store, Microsoft Store, and check out the app yourself after the talk. The source code of Shaper 3D is around 1 or 2 million lines of code, mainly in C++ with a bit of C and C# and Swift for the UI elements. I counted 58 open source direct dependencies of Shaper 3D, and these are just the direct dependencies. Of course, if I would count the transitive closure of all the dependencies, this would be a much higher number. And I found that around 50% of our code is not our code because it's open source. But this is not surprising because not so long ago, Shaper 3D was a startup, and startups usually don't reinvent the wheel, but use something existing. So did we. We used some open source software, and some of them stuck with us even to this day. Some of these libraries are very simple to use, very easy to maintain and integrate. For example, in C and C++, you have this thing called single file headers, where the whole library is just one text file. It's very easy to use. You just download the file, you include it in your CPP files, and there you go. You can use it. You don't even have to link anything. It's very easy to use. And there are some other libraries that are hard to use. And sometimes they are hard to use because we made it hard for ourselves. This time I'm going to talk about Google Filament. And we made it hard because we forked this library and we kept extending it. And well, we'll see the details. But the big question is, was it worth it using this library? Let's start. Before answering the question, let's jump back to 2021. We had to implement a new feature, a new display mode with more fancy shaders, more fancy lighting, new materials like this emissive material that you can see in the video. And the important thing was that this new display mode and the old display mode, we have to be able to switch back and forth quickly. Yeah, there were a couple of features. Yeah, you can go check in the application yourself. The important part is that this was a very rendering heavy feature. And apart from the rendering features, there was a lot of tasks to do to deliver this feature. For example, we had to implement a sidebar for the material browser and a bunch of other new UI elements, user workflows, UI layouts. We had to change the business logic. We had to think about how to monetize this feature because it wasn't a free feature. We added paywalls. We had to think about telemetry. How are we going to use telemetry to make this feature successful? So a lot of things to do. And on the other end, we wanted to raise money. And what better way to raise money than to make some noise on the market with a big marketing event. So what we did is that we set a marketing event in advance, and we had to deliver the feature by the deadline. So there was a deadline. It was a quite hard deadline. It would have been a big face loss if we couldn't deliver. So we did what you have to do. We cut the scope, and ironically, we cut the rendering features from this rendering heavy display mode. That means we weren't going to implement shadows in our application or new material parameters like normal mapping or new lighting effects like this reflection you see on the corner or new post-processing effects like depth of field. None of those were going, we didn't want to implement any of these. So we started looking for an existing solution for our problem, and we knew that we wanted something real-time, something fast. So we could make some trade-offs around visual fidelity. It doesn't have to be photorealistic. We resorted to something that's very often used in modern video games. It's called physically based rendering, and it's something fancier than the usual flat shaded CAD models, but it's not as fancy as cinematographics, for example. And since the majority of our users were on iPad back then, it would be nice if this existing solution would be available on mobile devices. And we came across an iPad app that looked just like what we needed. It was called Cadmio, and we checked how do they do rendering in Cadmio, and they were using an open source library called Google Filament. We really liked this library, so we started checking if Filament is a good fit or not. From a technical perspective, it was a good fit because it was written in C++, like the majority of Shaper 3D, especially the rendering code of Shaper 3D is written in C++. It supported the same platforms, iOS, macOS, Windows, and performance seemed acceptable based on Cadmio, which is an important factor for a rendering engine. Okay, what else? Code quality looked okay. Actually, it looked good. Yeah, the build scripts were easy to use. It was well modularized code. It used modern C++, good test coverage, and the sample applications enabled you to test the individual features. Yeah. It was also actively developed. It's developed by Google, by a team of 3 or 4 people, and they are very open to GitHub issues. If you raise an issue, or if you want to open a PR, they merge a lot of PRs. So this was good news for us because we knew that it didn't have all the things we needed, and we were expecting to open pull requests. And it has awesome documentation. I think one of the best documentations I have seen. And it's not just me saying that. I have seen other people praising the documentation of Filament. It's very good. And the licensing was permissive enough to use for commercial use. And the biggest selling point was that one of the sample applications was a GLTF file viewer application. GLTF files are rich mesh formats, meshes with fancy materials like in the picture. And the good thing about this is that our technical artists could already start authoring material assets and environments and baked lighting maps long before Shaper 3D supported any of these. So we could work in parallel from day one. So we decided to use this library. We met our deadline, big thanks to Filament. Released the feature in about 6 months. And the question still stands, was it worth it? At this point, the answer would be an obvious yes, because it enabled us to meet the deadline in a business critical situation. We will see what it costs us in the future. Okay, first things first. As I mentioned, many of our users were iPad users, and we are very keen on good performance on mobile devices. So we always want to keep memory usage as low as possible. And I also mentioned that we want to be able to switch between the old and the new display mode seamlessly. But the problem was that we now pulled in a new rendering engine. We had our own engine and the new one side by side. And there are these things called vertex index buffers, which have a bad reputation of using a lot of memory. So we wouldn't want to duplicate all these buffers just for the sake of accessing them from both rendering engines. Obviously, we want to share them if possible. The problem was that it wasn't possible to share it, at least not out of the box. Filament didn't support importing any kind of buffers. But this is fine, this is open source software, so we can extend it and add this feature. And we did add this feature. And we added a bit more. There were a few texture formats. Filament supported compressed texture formats, just not all of the ones that we wanted to use, so we had to add some. I mentioned Filament supports Windows. Okay, but Shaper 3D is not a regular Windows application, it's a universal Windows platform application. UVP is an application framework for sandbox applications on Windows, and Filament didn't support this platform. We had to add support. And the similar story on Mac with Mac Catalyst. And we added a few more features, improvements, bug fixes. We kept adding them. And by the time of the first release that I mentioned in one of my previous slides, we already had 44 PRs and 6,000 lines of code of divergence in our fork, which is a bit much. We wanted to reduce it. And also, we were very, very grateful for Filament. So we decided that, okay, some of these changes that we made, this could be upstream. This could be useful for everyone, not just us. So we had a Zoom meeting with the maintainers who were very happy to accept most of our changes, not all of them. We discussed what is useful for them, what is not. But we decided that we will open PRs one by one, and we will try to upstream as much as we can. And a few PRs went in quite easily, but not all of them. And there is a good reason. Filament and Shaper 3D is different in some terms. For example, the main platform for Filament is Android. Android drives all the technical decisions for Filament. And the main target use case is augmented reality. Whereas for Shaper 3D, it's CAD modeling. And our most important platform was Windows, because most CAD seats are on Windows. And this is a difference that sometimes caused some of our changes to be rejected. And similar things to this is supported devices. Filament had to support 32-bit devices. Shaper 3D doesn't care about 32-bit. So we made some changes that would have increased the register width of the C++ code. The code would use one more register, which is not so okay on 32-bit systems where you have 8 general purpose registers. If you use up one more than you should have, that's a significant performance issue. So they rejected it. On 64 bits, you have more registers, and also we accepted this in our code. But this is a place where our vision was not aligned. Another example is binary size. The Filament team is very, very adamant on keeping the binaries small. I guess this is also because of Android. Yeah, we like if binary size is small, but we are not that concerned about it. So some of the changes were rejected because of this. Okay, but in around 6 or 7 months, we managed to merge 15 PRs, reduced the divergence as much as we could. But around Thanksgiving, communication started to slow down, and okay, we thought this might be just holidays, but after 1 or 2 months later, communication kind of stopped. And I think we will see, maybe we made some usual mistakes that contributors do. Maybe it's because we have different visions, Filament and Shaper 3D, but both sides kind of gave up. By now we have almost 200 PRs and more than 7,000 lines of code divergence. And the problem with this divergence is that it discourages keeping your fork in sync with the upstream. For example, it took us 2 years to make our first bump. And even when we did it, it took 3 weeks plus bug fixing. And I think this was even less than we anticipated. We were so discouraged from bumping. And after these 3 weeks of blood, sweat, and tears, well, we weren't encouraged to do it again. I think we bumped one more time after this and haven't bumped since. Why is it a problem? If you don't sync, of course, you don't get the fixes and the new features. I would say we are less interested in the new features right now, but bug fixes would be welcome. Especially because sometimes you need those bug fixes. There are some situations where you're forced to get them or somehow obtain them. For example, if there's a security vulnerability in this library, we have to act on this and we have to do something, and we have to do it quickly. So either you are forced to bump or at least cherry pick the fixes from the upstream. And the same situation when we keep using new and new SDKs, we bump Xcode, Visual Studio, and so on. Sometimes build scripts break, and those build scripts probably don't break on the upstream because they maintain it, they fix it. But if you don't sync your fork, you don't get those fixes. Again, you can decide if you cherry pick or bump. But this is not an ideal situation. One more thing I wanted to mention is that I talked about how we shaped Filament to our needs, but sometimes it was the other way around. And one particular example I can remember is when we had a performance issue. As you may know, rendering works the way that CPU sends commands to the GPU executes them, and tada, you have a picture. And the less commands you send to the GPU is generally the better performance you get. So usually rendering engines do something called draw call batching, which means that they try to draw as much with as few draw calls as possible. And our rendering engine had a very aggressive batching strategy. The problem with this strategy was it wasn't reusable in the other engine, in Filament, that we pulled in. And it would have been a big change to Filament if we wanted to somehow reuse it there. And we already had a lot of changes in Filament, so we didn't want to diverge even more. So this time what we did is we ended up changing our batching strategy to fit both rendering engines at the cost of losing some CPU performance. I have to mention that we lost some CPU performance in our own rendering engine, but before this, the other rendering engine had no draw call batching at all. So we won a lot more performance back there. So it wasn't a bad trade-off. And we didn't have to touch Filament this time, which was a big win. Okay, as for the future, we have realized that we cannot reduce the divergence to 0, mainly because we have different roadmaps. We think that we are very unlikely to find a better fitting physically based rendering engine, I mean a third-party lib. Probably we will not replace it. Probably we'll use it until we can. And when we cannot, we have two options. We either fully detach our fork, because our fork right now is a regular GitHub fork. We can always sync it to the upstream, we just don't do it, but we could. But we could totally detach it, I don't know, even rename it, and then we do what we want with the code. Or the other option is that we write our own physically based rendering engine, which is a big work. We tried to assess it, and even that took weeks. So I don't know when or if ever we are going to do it. We'll see. And this is all I wanted to share. The key takeaways I want you to remember is that open source helps you to move fast. It did for us. And free software is not free, as we already heard. It cost us a lot of engineering hours. And also, I wanted to mention that if you use open source software, be grateful. If you fix something, always try to give it back. And the last point is that you might get logged in. This is not specific to open source. You can get logged in with any third-party dependencies. We did a little bit, but that's fine. Thank you for your attention.